So it's a privilege to be here today. I've heard a lot about this group over the years, but I've never been able to attend this auspicious group's meeting, so it's good to be here. I want to thank Pete for bringing me in. Myself and my colleagues are, again, with the Geological Survey. Due to sequestration, none of us can really travel. So thankfully, I was able to get some help to come here, and because I am required to say this, I apologize. I am not representing the survey, the Department of Interior, or U.S. government. I am here on my own time, off duty. So anyway, it's okay. I was not looking for an applause. No. It's always great to stay involved with this group. So what I want to talk about today is really something that's a little bit of a hobby with some of us, a small group of us in the National Water Quality Assessment Program. The NAWQA program's been around for about 20 years now, and I think in the very beginning, we recognized that you cannot really assess water quality without assessing water quantity. But over the years, we've really struggled with, well, how do you assess water? How do you assess, how do you assess whether the water in a stream is what it should be? How do you assess the natural flow regime? And that's really what we've been working on the last 5 or 6 years. We just published a report just a couple of months ago that sort of summarizes a lot of our work in flow and in other areas, and you're welcome to dig that up or contact me and I can send you a hard copy. Again, what we were really trying to achieve is, how do we really determine whether the natural flow regime is being achieved at a particular stream site? And really, to get at that, we have 3 basic questions we have to answer. The first of all is, well, what is the natural flow? What should the flow be at this stream X? And again, we work by definition across the whole country. And so we have to be able to answer this question just about anywhere. And so we can't really invest a whole lot of resources into one watershed. We have to look at the big picture. So what are the natural flows that we expect? And then how do those flows vary through time? We know that there's a tremendous amount of annual variability in stream flow that's just due to natural fluctuations in precipitation. And if we can get these first 2 pieces, then I think we can go to where we really are able to integrate an assessment of flow alteration with assessments of chemicals and other stressors that might be affecting the health of a stream in any particular place. And so that's where these are the questions that inspired a lot of our work. And so really what happened is we were working on this at the national scale, and then Pete and Jeanette Howard and some others saw some of what we were doing and convinced us to sort of do some stuff on the side for California just to see if we can make it work at a smaller scale. So really what you're seeing today is a prototype or a hobby, and again, the idea is if pieces of this seem useful, then we can probably figure out ways to expand its use. So keep that in mind, please. All right, so what do we mean by stream flow? And there are probably over 500 different statistics and metrics that people calculate from a stream flow time series. It's bewildering. And I think in many instances it's confusing and it actually works against us because it just seems overly complex. We started from the premise that, well, we know that we're not going to be able to predict daily flows at places where we don't have gauges. There's just, we don't have it requires too many resources to be able to try and model that. So let's try monthly flows. Now the advantages of dealing with monthly flows is that we still have some indication of seasonality and magnitude and frequency if you look at monthly flows over a long period of time. I would also argue that monthly flows are easier to communicate than something like the annual skewness. Okay, how do you explain that to the public, right? Or the 7Q10, although that's probably one that a lot of people understand. So there's a lot of metrics out there that we just thought were just too confusing. Let's stick with monthlies. And I think if you don't have a gauge, I think a monthly flow is a reasonable thing to actually estimate. You could probably pick a few days randomly in the month, go out and take a point measurement, and you can probably get pretty close. And what's nice also is that monthly stream flows are synchronized with a lot of the historic precipitation data, like from PRISM and other sources. You know, from my understanding, maybe my sources are wrong, but a lot of the historic precip data is really summed or sort of aggregated at the monthly level, and getting that disaggregated to smaller time scales is a real problem. So that's another pro. Now the downside of only looking at monthly flows is that you're sort of ignoring a lot of other aspects of the flow regime that we know are important to biology, to ecosystem health. And so we do have ways, and we have actually have a few publications where we have predicted some of these other attributes of the stream flow. So, but I want to talk about monthly flows today. Now, so if we're talking about trying to predict natural flows, really we have to start with this with a network of gauged watersheds that are hydrologically undisturbed and that have a fairly long period of record. Well, it turns out there's about 163 of those in and around California. Not all of them are currently active, and these are USGS gauges, and I think maybe there's probably a few more if you add in some state gauges. And again, not all of these are active, but this is the sort of the data set that we can start with to build some of these models. Now, the kind of models we're talking about are not rainfall runoff models, they're not mechanistic models, they're statistical models, mainly because we have a lot of information we can use, and again, the rainfall runoff models often require a lot of calibration at smaller spatial scales, and we just don't have those kind of resources to do across the country. And so because we're talking about statistical models, the whole issue of regionalization comes up. And where we've played with these models in different parts of the country, what we've found is that the larger we go with the spatial or with the geographic extent of the model, the larger that extent is, the more that the variation that we're trying to model is really just overwhelmed by big scale longitudinal climatic patterns in different parts of the country. And so to the degree we could, we thought, let's try, if we're going to do this for California, let's try to go as small as we can in terms of a relatively homogeneous hydroclimatic space. But of course, we still have to have enough reference sites to build models and work with. And so that's sort of tugging at us from the other direction. So we played around with this for a little while, and I think where we landed was we combined a couple of level 3 ecoregions, and I'm going to call those the North Coastal Mountains. And then we combined a couple more regions, and we're going to call those the Interior Mountains. And you know, to some degree, that makes sense hydrologically to sort of treat these separately. And then basically everything else was the xeric from our perspective. And what this gave us was about 60 gauge sites within each of those regions. And I'm not arguing that everything within those regions is homogeneous. I mean, it would be nice if we had 200 gauges within each of those regions. That's just not going to be possible. So anyway, those are the regions that we started with. So what do these models look like? Just to think of it in terms of a dependent variable, and I'll lay out what the different predictor variables were. Again, we're trying to predict a monthly mean Q, or stream flow. It's the average flow over a month. And we were trying to, and we built the model so that we could predict these monthly flows for a specific year. Okay, so that was the dependent variable. And then we had a series of independent variables that varied through time. We had runoff, precipitation, and temperature all aggregated at the monthly time step. Runoff is basically something that we generate. We basically have a national grid that basically calculates runoff by incorporating precip, temperature, ET, et cetera. So there's a lot of redundancy among these predictors, but those are the three we had, and these are all from PRISM data. And then, so we had those for T minus 0, so for the month that we were trying to predict. So if we were trying to predict June of 2005, we would have runoff, precip, and temperature for that month. But then also the 12 preceding months, okay? So there's 39 predictor variables already, just to predict June of 2005 flows, okay? And every year, of course, those predictors are going to change because they're sequenced through time. And then we have about 90 static predictors, different physical characteristics of the watershed, things like geology, soils, topography. I also, just for kicks, threw in some long-term climatic data, things like long-term average precip and air temperature, because there may be some long-term climatic variability still in the model that we can't explain with some other variables. So these are what the models look like, and we basically built the models from 1947, not 50, to 2012. So we have about 60 years that we went back, and these are all referenced, hydrologically least disturbed sites that we tried to build these models. So the statistical tool of choice is one that I think is seeing a lot of action these days in ecology and bioassessment. We picked this method mainly because it's for the most part assumption-free. We don't have to worry about a lot of the baggage that you do with linear regression or multiple regression. But what we found is really useful is the fact that this statistical technique really explicitly models nonlinear relationships between your predictor and your independent variables and interactions. We know that soils and climate interact to produce flow. So, this kind of modeling framework was good. And then random forest also, in many cases, resists overfitting for a variety of reasons. But we've tried, we've done a lot of comparisons between random forests and other modeling techniques, and we just found that this one, at this point, still comes out on top in terms of performing better than some of the other methods that are out there. Enough about the statistical mumbo-jumbo. So how do we measure model performance? Again, we have roughly 50 to 70 reference sites per region, but if each reference site is represented in our data set, basically the number of years that it has in its record. And then ideally, what you would do is of course, withhold 30% of your data, build your model, and then validate the model on those data you withheld. We don't have that luxury with 50 to 70 sites. So we used a jackknife technique where you basically pull one reference site out, build your model, apply the model apply that reference site to the model, make predictions, and then sequentially go through and do that for each of the sites. And so that's the method that we used. And then we used a variety of, if you look at the literature on measuring model performance, there's all kinds of suggestions, and I'll explain a couple of them as we go along, but we did look at lots of different measures of model performance. So how did we do? The most straight up, I think, measure of model performance is the R-squared between what you predicted and what you observed. And again, this is for the jackknife observations. And so, again, we have 3 different regions, and we have a model for each month, right? So how did we do for the xeric? Here's what the R-squared values were in the xeric. And you can see that in general, we're explaining about 2/3 of the variation in monthly flows, with a couple of exceptions like October. But for the most part, nothing to slouch at really. The models are much better for the interior mountains, where we're explaining in general 3/4 of the variation with our models, and they get even better in the north coastal mountains, where we're explaining generally 80% or more of the variation. If we really truly used a more rigorous validation technique, these numbers might go down a little bit, but still, these are, with jackknifing. So I think we're pretty confident that these are true measures of how good these models work. Just another measure. So here, again, so here's an example of Willets Creek. I'm not sure where that is. Somewhere in California. We would withhold that site and build the model and then put that site into our model. And what we would get then out of that is an observed and a predicted through time. And I think this is maybe September. I forget which month this is, but this would be for a given month. And so then we simply look at that ratio of observed and predicted through time, and we average that out. For this side, it should be 1, and for this side, it was pretty good. And so we average that across all of the reference sites, and that's another measure of how the model performed. And so using that for the xeric region, most of the models are right up there around 0.95, 0.9 in that region. in that area. Interior mountains, about the same, maybe a little worse in some months. North coastal mountains were just screaming good, almost always very close to 1. What you notice here, again, these numbers could have gone higher than 1, but none of them did. And part of that, I think, is an artifact of random forest. I think there's some stuff with random forest that might prevent us from going over 1. But the other, I think, reason is that there's probably some characteristic in the watershed that causes loss of flow that we simply can't catch with the predictor variables we have. And so in general, we tend to over-predict the monthly flow by about 5%. And we're down where you see these bars kind of well below 1. That's about the bias that we're getting, is about 5% over-prediction. So I don't think that's a big problem if we just keep it in mind when we're using and when we're applying models like this. We just have to be cognizant that we generally tend to over-predict by 5%. I wanted to give you a quick summary of what predictors were important for these monthly flows. So what I did is I kind of lumped the monthly flows into groups, or the predictor variables into groups. So this variclimate, or those time T0 through T12 variables that vary, and then the average climate, and then I basically lumped all the soils, topography, and geology together. And again, for each region, we built 12 models, 1 for each month. So in the xeric, of course, those time-varying climate variables were always important, but then topography was important in a lot of those models. Geology didn't seem to matter in the xeric region. I don't know enough about the systems or the area to know if I trust that or believe that, but that's nevertheless what we found. Interior mountains, geology and soils were a lot more important than they were in the xeric. And then for the north coastal mountains, what's interesting is that long-term average climate was a big factor. So there's something about the long-term climate that we weren't able to capture with those time-varying climatic variables, and so it was probably a good thing in retrospect that we put in, that we considered those long-term variables as predictors. So overall then, I think we can with respect to our first question, we can do a decent job at predicting monthly flows. I think we're pretty confident that we can pull that off, at least going back to 1947. So the next question was, how do these change through time? Can we really see this? And in fact, I just pulled out Cucamonga, is that how you pronounce it? Cucamonga Creek? What a name, that's great. And here's the September mean flow, and I went back through 1968. And here's basically the model predictions of mean flow in September for Cucamonga Creek in this particular reach, whatever reach that is. We can find it on a map, but you can see there's a lot of zeros. And so you can sort of, one way, and I'm going to show you in a minute a map that we generated, but basically one way to look at this is just say across this whole record, what proportion of the time, what proportion of years was September flow greater than 0? So was as a measure of perennialness, okay? And when you do that, I did that. Is that the next one? No, I'll get to that one in a minute, okay? Here's another way to look at it. I just randomly picked a network of stream segments. This is NHD version 1. This is somewhere in California, sort of in the coast area. We can project our predictions for every stream segment now, because all of those predictor variables we talked about, we have them for every segment in NHD. And so I'm just going to kind of go through this. This is 1980 to 1989, and you can just kind of see how from one year to the next, and this is actually April flows, but it could be anything, but you can see how from year to year, these expectations of natural monthly flows vary a lot, both in space and in time. And so this is something that we can use, I think might have some important implications and uses out there. Okay, so here's that map I showed you. What I did is I took every segment in the xeric region, although I left out the mountainous areas in the south there. I just inadvertently forgot to put in the code for whatever ecoregion number that was, so pardon that. But basically every segment in the xeric region is represented by by a color of basically the proportion of all the years going back to 1947 when April flow was greater than 0. So when there was flow on average in April. And then I just arbitrarily picked these 3 breakpoints. But I think that the usefulness of this kind of approach is that we haven't made any kind of, I don't think, any arbitrary decision about what does perennial or what does intermittent mean. And I think it gets at what Pete was talking about, where let's treat perennialness or intermittency as a continuous variable. And in this case, it's really sort of a probabilistic statement about water during that month, and we could do this for every month. And what's interesting is, at least in the Xeric region, only about 20% of the reaches were in this category of 0.67 to 1. So in other words, 75% of the reaches had flow, in general, less, your chances of having it being that segment being dry in April are basically 60% or better in any given year. Okay, so I think we can do a decent job then of going back in time and looking at how these natural flows vary through time. And it presents some interesting and I think some potentially useful products or tools that we can use to visualize monthly flow. How do we get at this flow alteration question? And I think one way to look at I think the most reliable way to do this is to start with the about 700 USGS gauges in California that have at least 10 years or more of record from the 1990s. There's nothing magical about 10 years or 1990, but there's a lot of USGS gauging sites where we measure flow. And so for starters, we can go to those sites and compare the observations with what we expect naturally. And here again then is Cucamonga, my favorite stream. And here is the same plot I showed you a minute ago. It's scaled differently, and you'll see why in a minute. But there's the estimated natural monthly September flows from 1968 onward. Well, what did we actually measure at that stream gauge there? And what you can see is that in the 80s, something very drastic happened. And I don't think it was the haircuts or MTV. Actually, what happened at Cucamonga Creek in the late 70s, early 80s is concrete line channelization and a POTW releasing upstream of this particular site. So we can do this kind of analysis with all those 700 stream gauges. And something that's talked about in an earlier talk, we can then build statistical models again with these flow altered sites and say, now, can we, with measures, with geospatial measures of human impact like reservoir storage or urbanization, can we actually predict or sort of spatially forecast, if I can use the word, where we'll probably see altered flows? So instead of predicting natural flows, we're predicting the likelihood of altered flows. And we actually tried this, haven't tried it in California yet, we tried this in the South Platte River Basin. That looks very interesting when it's rendered on the screen, but that's the whole network of NHD plus segments of the South Platte River in Colorado. And increasingly dark number is basically increasing likelihood of depleted flow, and I forget which month this might have been, but the diamonds are actual gauge sites. But this kind of approach, again, could also provide a useful way of visualizing where we're likely to have altered flows. Now, of course, the downside of all of this is these models are only as good as the predictors that go into them, and we all know that geospatial variables that really capture water use are pretty lame. But I think maybe in California they're probably better than in a lot of other parts of the country. So when we try this in California, we might actually do a little better. So that's all I had. I want to thanks for your attention, and if there's time, we can do a question or two. I have to tell you, I'm not a hydrologist. I forgot to say that at the beginning, so don't ask too many hydrology questions. Thank you.
Thank you. Could you tell us a little bit more about any modeling you might have done with respect to anticipated changes from climate change? Maybe amplify that a little bit. That's certainly something on our mind. Thank you.
Yeah, I knew someone would ask that. I should have prepared an answer. No, that is a very logical next step here, because really the most important predictors for these monthly models is really the precipitation that happened that month or the previous several months. So it would not be at all difficult to start then applying some climate change predictions of how those precip and air temperatures might change. We could definitely play those games. We haven't done that. Like I said, this is a part-time hobby for a small group of folks, but certainly the application to climate change did not escape us. It's definitely worth doing.
So many questions. Great presentation. It's amazing that this is a part-time hobby when it seems like this is such a high priority issue. So that's just, I guess, a comment, but thank you. Okay, yes/no question, and then probably a more difficult question. Yes/no is, have you compared, for example, let's say your September or October flows to the data in, say, NHD or one of the other databases that has, things coded as perennial, non-perennial, and have you looked at how those compare? And I'll just go ahead and say the second question. What, if any, bias do you think might exist in the model just based on where USGS gauges are located? My first guess is that I'd expect to be more difficult to predict in small basins and headwater streams, just because those aren't gauged as frequently.
Let me answer the second question first. The issue of everybody knows that stream gauges were not placed on the landscape randomly. What we can do now, though, is that because we have watershed features for every watershed in a region now, we can compare the watershed features at the gauge sites with the universe, with the population. And when we do this, what we consistently find is that the overriding bias is stream size. And so we have to ask ourselves, well, if we believe that what we're modeling can be scaled down, then maybe we have some confidence in what we're doing. But then the other argument is simply, well, what else are you going to do, right? We might have to simply be cognizant of the fact that when we're making predictions for very small segments, that there's probably more uncertainty. And that's uncertainty we can quantify. But yeah, that's a good question. Your previous question was I forgot it already. Oh, the NHD, that's right. I have to be careful how I answer that because, NHD is a wonderful thing. We tend to not use those predictions or those data that are in the database. They were built with very crude. I think the measures like mean annual flow are probably pretty good. But beyond that, I wouldn't trust a lot of that stuff. And we haven't explicitly compared the perennial, non-perennial, but I think Pete's group has and others and found that just don't even use those perennial, non-perennial values in NHD. There was a question up here.
So, is this on? Okay. Are you sure? Okay. Oh, I didn't put it close enough. So, how would you factor in El Nino and La Nina events? Because those phenomena can actually put the coastal weather really out of whack. And where the North Coast region might, let's say, be occasionally wet, then one year it's suddenly kind of like Southern California, where it's dry all the time. And it could be like that for 1 or 2 years. How would you factor those into your predictions?
Right. Well, I guess one response to that is that in a way we sort of have, because when we do a prediction for 1983, we're using the precipitation that occurred in the previous 13 months. whether that was wildly out of normal or not. But what we have noticed that's, I think, related to those cyclic events is that there are some years when our predictions for some sites are way off. And what would really be interesting is drilling in and seeing, okay, are these maybe some of these really strange wet years? And if so, then maybe that's another flag where we can say, okay, if it's a really strange precipitation year, then be careful. So, but that's a good question.